We are Team 1 and we are presenting Ceres Sample Return Mission. Our team consists of, from left to right, Alex Vakian, Eduardo Garcia Rogel, Melody New, myself, Cynthia Sanchez, Brandon Seguic, and Melissa Ventura. Next slide. Here is the outline of what we will be presenting today. It includes everything from our mission overview to our final design. Next slide. Our mission is to have our spacecraft depart from Earth to a Ceres rendezvous and polar orbit insertion, land and ascend to retrieve samples from Ceres, and return to Earth. Our requirements are to launch between 2035 and 2045 with a mission duration of more than 12 years. The spacecraft is not allowed to travel below 0.6 AU with respect to the Sun, and it is required to have a dry mass of 1,200 kilograms. 2 trajectory designs are required, 1 impulse transfer option, and 1 low thrust trajectory. Next slide. Our first trajectory is the impulse mission. It has a total mission duration of 6.13 years. Our second trajectory is a low thrust mission. It has a total mission duration of 10.22 years. Both trajectories fall within the required mission duration. Next slide. This is the basic trajectory of the first mission. It departs from Earth, arrives to Ceres, and returns to Earth. Next slide. This is the basic trajectory of our second mission. It departs Earth, does a flyby with Mars, arrives to Ceres, and returns to Earth.
Ceres is an extremely interesting body for study by future space programs. The bright surface spots on Ceres, which were previously observed by the Dawn spacecraft, indicate possible remnants of saltwater on the dwarf planet, which scientists believe could be due to an internal ocean within the planet. This makes the prospect of performing a sample return mission to Ceres and back an important step in furthering our understanding of the habitability potential throughout our solar system. Our objective to reiterate our mission design goals explained in our requirements, and some of the software we utilize to design our mission include MATLAB, Malto, and JPL's Horizon system. Next slide. Some of the assumptions we made when modeling our design include that we've assumed that by the launch date of 2035, technology will have advanced so that obtaining 50 kilowatts of solar panel power will be feasible. We also assumed when calculating the mass of propellant, delta VD and VG are negligible, so our equation can be simplified as shown. And the gravitational parameters listed in our key physical constants are measured at the surface of each body or the sea level for Earth. Some of the theories we utilized when making our calculations included Holman transfer theory, Lambert's method, and the method of patched conics. Next slide.
So now we're going to talk about our impulsive trajectory. Our impulsive trajectory has a timeline of 6 years and 47 days, starting on April 15th, 2036, and it includes a full year stay at Ceres, including a landing mission to collect surface samples. So for our launch vehicle, we decided to use the Delta IV heavy lift launcher because it can take a payload mass of up to 14,220 kilograms to GTO and only costs about $350 million. The interplanetary stage will use the RL-10C engine because it is lightweight and has a high enough thrust to assume an impulsive trajectory. For the landing module, we've included a chemical engine capable of 418.8 kilonewtons and should be able to land on Ceres. Here's a table of when each leg starts and the trajectory properties at each time. These trajectories were calculated using the MATLAB codes in the appendix of this presentation. And a few key notes are that the total mission time is 6.13 years, as previously stated, and the total mass of the propellant is 7353 kilograms, and the total delta V is 26.5 kilometers a second. We also did not leave any extra fuel. However, the current mass margin would allow for extra fuel if necessary. So here is a departure energy plot for the leg to Ceres. It shows an optimal departure and arrival date of April 15th, 2036 and May 19th, 2040, respectively. Here's our departure energy plot for the leg back to Earth from Ceres. Notice that the optimal point we used is askew from the middle of the plot and thus requires more energy. This is because we wanted to arrive at Earth with a V infinity of close to 6 kilometers per second without a braking burn. This point achieved the lowest arrival velocity at Earth while requiring minimal escape energy at Ceres.
As you can see on this slide, we are showcasing the breakdown of a timeline for the low thrust trajectory. Our departure date from Earth to Mars will be on April 21st, 2035. We will use Mars as a gravity assist to travel to Ceres and park for 365 days. Our arrival date to Earth will be on July 8th, 2045, and the total duration of our mission will be about 10 years and a quarter. Next slide. In the next couple of slides, we will be going over the technical calculations and analysis for the low thrust trajectory. We will be using the same launch vehicle as the impulsive trajectory, which is the Delta IV Heavy. For our engines, we'll be using two of the NASA's evolutionary xenon thrusters with an ISP of 6,500 seconds. Our landing and ascent module will be the same as the impulsive trajectory. Next slide. Here you can see the different legs for our mission. On the right-hand side, you can see some of the screenshots for our plotted missions, which were created by Malto with a 2D and a 3D view. Next slide. On this slide, you can see the remaining legs of the mission. At the top, we listed that we will be collecting a maximum of 5 kilograms, which we did take this into account when executing our trajectory. At the bottom, we listed our mission totals, such as our total mission duration of 10.25 years, total fuel burned of 1,225 kilograms, total fuel left over of 2,248 kilograms, and the total V infinity required of 11.88 kilometers per second. Next slide.
So the following proshot plot shows the Earth to Mars departure and arrival dates. These were used as initial guesses in Malto. We show a departure date of July 20th, 2035, and an arrival date of October 7th, 2036, with a C3 energy of 28.1 kilometers squared per second squared. Slide. Another proshot plot from Mars to Ceres is shown below for the initial guess dates. The departure date matches the arrival date in the previous plot of October 7th, 2036, and shows an arrival date to Ceres on June 10th, 2040, with a C3 energy of 28.6 kilometers squared per second squared. It is important to note that the C3 energies of these two plots match as we do a flyby through Mars. Slide. This shows the Ceres to Earth proshot plot. Initial guess dates. The departure is December 20th, 2043, and the arrival is April 23rd, 2045, with a C3 energy of 28.8 kilometers squared per second squared. For these proshot plots, initial guess dates, we assumed an upper and lower bound of 60 days. Slide. Here we show the Ceres landing site, and we chose the Dontu crater. The Dontu crater is 22 degrees north and 133 degrees east because of its location within a low-flying region named Vendemia Planitia, which has been proposed to represent an ancient impact basin. Dontu possibly offers a window into the composition of Ceres' deeper crust, which apparently is enriched in ammonia. Slide. Here's an overview of our Delta IV heavy rocket, which was chosen. It has a payload to low Earth orbit of 28,790 kilograms and a payload to geostationary transfer orbit of 14,222 kilograms with a vehicle mass of 733,000 kilograms. It was chosen due to its high payload to GTO, as it will allow spacecraft mass to increase in the future if needed. Slide.
To finalize our design, the team confirmed multiple important aspects of both trajectories, which can be found on the slide. Please take note of the important differences in both missions, specifically the type of propulsion system and propellant used, the overall fuel left, the total mission duration, and the use of a gravitational assist. Next slide. Finally, the team was able to develop an approach to solve and meet every requirement that was placed for this project, except for the final requirement number 12, which we will see in the next slide. Next slide. The reason behind not meeting requirement number 12 was due to adding unnecessary complexity to the missions. Considering our designated landing site is determined to be sample-rich with 3 different types of material, it was determined one landing site was sufficient in bringing back multiple types of samples. Therefore, multiple landing sites was deemed unnecessary. This brings us to the end of our presentation. Thank you.